Okay, we will start the discussion in the following way. So we will take a slightly more general setup than is immediately called for. It will help us later. The idea is this, that we have a model like this, that y equal to x beta plus epsilon. Now what I shall do is that I will consider this x and split it up into two parts. So I have got x. I will split it up into two parts. Suppose I call it x1 and I call this x2. So x1 is, x is made up of x and x1, and I am interested in knowing how much does x2 help to explain the behavior of y when x1 is already part of the model. So basically, as if we have already fitted the model using only this x1 part. So if I write the beta thing, then you obviously have similarly the beta 1 part and the beta 2 part, two vectors. So this is like you have x1 beta 1 plus x2 beta 2. My question is, if instead of fitting this, I had fitted this model and some error. So this error is possibly different from that error. So if I just fit this model, I have already explained part of the behavior of y in terms of these inputs. Now, how much justified is the inclusion of x2? So that is the question that I want to answer. And this will lead us to an efficient way of scaling that residual sum of square. Okay, so this is primarily based on the same diagram that we have seen earlier. Namely, we have this situation. So we have got this thing. I have got this column space of x. This is the entire thing, and y, and that residual vector. Now I have here introduced a new thing, which is x1. So it's a subspace. A column space of x1 is a subspace of this pink space. So I have something like this. So I have shown it in this way. So this part, so this thing is actually column space of x1. So in my picture, I have column space of x is a two-dimensional object. So the only way I can split it up into two parts is by showing one-dimensional subspaces. So this is my one-dimensional subspace, this blue line which passes through the origin over there. So the question is, if I use only that blue line, of course I will be able to explain less of the behavior of this green arrow, but how much less? So that's what I want to answer. And for that, what I do is the natural thing. I will just consider that if I take only this blue line, that is only column space of x1, then let us try to fit the model. Which means then I will have to drop a perpendicular from the tip of the y vector onto not the pink space but on this blue line. That's also a space. That is the column space of x1. So I have dropped a perpendicular here. So when I am using the entire x, that is the pink plane, then my error vector is this. When I am using the subspace, only the blue line, then my error vector is this longer arrow, which is of course expected because see, if I have restricted my x space, then the residual will naturally go up. Now the question is, how do I compare? Now one way of comparing it is like this. I have already taken my x1 part into account. So I already have this. Let us see how much is the decrease in the length. So I will take this norm square of this vector. So this thing, you can see that this is a right angle triangle, so I can apply Pythagoras. So I can work out the norm square of this, which is nothing but norm square of this residual vector minus norm square of this residual vector, and that will give me this. So if I write it in terms of some mathematical notation, this is what I am doing. I am taking the y vector. From it I am subtracting pxy. That is the projection of y onto column space of x, which is basically this vector. That is from the origin to this, to the tip of this. So if I consider this means this residual vector. I am showing as this point. So I am considering norm square of that. Give it a name RSS, residual sum of square. Now I will also consider the part which is onto this. So now I am trying to consider this vector, this thing. This thing, when I am projecting it onto the blue line, that will be similarly y minus p x1 y. I consider this also. I might call it RSS1. And we can now argue like this that I have this vector, this RSS1. If I just include x1, that is sort of my simpler model. So this is the error that I am anyway committing. So keep your RSS1 downstairs, and in the numerator you look at the difference. So how much do you gain by including that x2 part? That is RSS1 minus RSS. RSS is always bound to be less than RSS1, less than or equal to. So consider this point. So this number, which you can easily guess, has to be between 0 and 1, because all these things are non-negative. RSS is less than RSS1, so this is always between 0 and 1. So this gives you a measure of what is the additional benefit of including x2 in the model when x1 is already present. But all this thing in a very crude sense, because you are judging a vector only by its norm length.